Oh, welcome back to MATLAB Programming for Engineers. In the previous video, we introduced the idea of a discrete time simulation for computing the solution to a simple differential equation. And in this video, we want to show how to apply that to a mechanics problem. So I'm here with my colleague, Dr. Aditya Jayakumar. So Aditya, how does this fit in to the structure of the course overall?
A simulation is modeling reality with some assumptions. Oftentimes, it is difficult or impossible to experiment, to perform experiments on every single combination of reality. And in those cases, you definitely need computer simulations to assist in this process. Sometimes the experimental process is too expensive. Sometimes it is not even possible. I had an old nuclear engineering professor who was advising me on modeling and simulations in the past. And he told me that, he models nuclear reactor safety. And he said, if everything goes well, he will never have experimental data, right? And we can all hope that he never has experimental data. Modeling things for the future, things which have never happened before, also will not have experimental data. So if you're modeling the spread of a virus during a pandemic, until you have it, you can go based on like previous pandemics, et cetera, but you still don't know exactly how this virus is going to spread without actually having a model in place. But one of the foremost things that you need to remember when you are creating any of these models is, first, are the assumptions that I'm making sufficient and okay to do, given that I'm trying to model a physical process? And second, does my model make physical sense? Because if my model does not make physical sense, then that is not a sufficiently good model. So I'm going to give it back to you, Jim.
All right. So what we're starting with is a really simple, essentially physics 1 kind of problem, just calculating the motion of a particle with constant acceleration. Well, at least we'll start out with constant acceleration, and then we'll elaborate the model a little more to handle variable acceleration. So the basic equations that we're trying to model are what you learned in physics 1, just from the definition of velocity and acceleration, that the velocity is the derivative of the position, and the acceleration is the derivative of the velocity. And just as we did in the previous example of radioactive decay, we replaced those differential equations by difference equations. In other words, the d's become deltas. And that allows us to set up an equation that we can put into a loop to run our simulation. Now, all the physics is wrapped up in here. What's the acceleration? So that's really the only thing that varies from one problem to the next. You have a different set of forces, therefore a different acceleration. And we're going to start out with the simplest possible case, just a free-falling object under the influence of gravity. Now, you might remember from physics 1, not only do you need those definitions of velocity and acceleration, you also need the initial conditions. And this is essentially a second-order system because it's two differential equations, or in some cases, they could be combined into a single second-order differential equation. That means you need two initial conditions. You need an initial velocity, you need the initial position. And of course, this is only a one-dimensional problem. It can be elaborated to a two-dimensional or three-dimensional problem as well. But similarly to what we did in the previous problem, you take that difference equation, you write it in the form of what's called a recursion relation. That is, you've got the velocity and the position at one time step, and you use that information along with the acceleration to calculate the velocity and position at the next time step. So you can imagine how this goes into a loop, and you just run this loop over and over again, and you get the velocity and position versus time. So here's a little flow chart illustrating that process. Of course, you're only going to have certain parameters that you need to set up. And one that we talked about briefly, and we'll come back and talk about it a little more later, that's a crucial parameter is the time step. What is the time between your simulated steps? And that has to be dictated basically by the physics of the problem. Set the initial conditions, calculate the acceleration based on the physics of the problem, and then you have a loop where you just apply this recursion relation over and over again. Now, in the first problem we're going to do, the acceleration is going to be constant. So we won't need this step, but as the problems become more complicated, we'll introduce effects like drag that'll give you a variable acceleration, and then you will need to update the acceleration as well on each time step. And the stopping condition is, well, how is the problem specified? How long do you want to simulate? Is it a fixed amount of time, or is it until some condition is reached? Exit the loop when that condition is reached, and then do whatever analysis you need to do. A plot, usually you're going to do a plot of the acceleration, velocity, and position versus time. You might calculate certain parameters, like what was the maximum velocity achieved, or how much time did it take for this to, the physics of this to play out. And that's it. All right, so let me show you how to code this in MATLAB. All right, so as I said, we're starting with the simplest possible problem, which you learned in Physics 1. You throw a ball up in the air, and it falls back to Earth. And for right now, we're going to neglect air resistance or drag. So the only acceleration we have is the acceleration of gravity, and we're assuming we stay close to the surface of the Earth, so the acceleration of gravity is constant. Right? So this is just going to be a constant acceleration problem. All right, so as I showed in the flow chart, first you initialize parameters, and really the only parameter we have here is the acceleration of gravity. Because we don't have drag yet, it doesn't matter what the mass of the object is. You learned that in Physics 1 as well, that the acceleration due to gravity is independent of the mass of the object. As I said, we need the initial conditions for velocity and position, and we need to decide what we're going to use for our time step in the simulation. And I'm going to start with 1/10 of a second. We'll see how that works out. So here's the essence, the guts of our program. This loop where we're going to update the position and velocity on each time step. Now in this case, it's not going to be a fixed amount of time. We're going to keep simulating until the object hits the ground. So that's going to be a while loop. Right, so what's the condition going to be? Well, for right now, let's keep everything as simple as possible, and then we'll add all the details as we go along. Basically, it's just as long as the object, or sorry, as long as the position of the object is greater than 0. And when that gets back to 0, that means it hit the ground. Now, if you think about it, if you're thinking ahead, you might realize that's not going to be quite sufficient. I'm going to need to add something else, but one thing at a time. So while this loop is running, what? Well, we update the position, and then we update the velocity. And so this is what we called, as we said, the Euler method. In fact, this is specifically the forward Euler method, where you update the position based on the velocity from the previous time step. And for the acceleration here, it's just a constant acceleration of g. So I'm just going to put g dt. Now, as far as the calculations are concerned, that's it. We'll need to add more details here as we go along so we can keep track of the position and velocity at each time step and be able to plot it later. But for right now, let's just do this simple scalar calculation. Now, the reason this condition isn't quite right is because we're starting out with y equals 0. So since y is initially 0, this condition is not going to be true the first time. The loop is never going to run. So we need to do something a little differently here. We just need to add one more little thing. Let's say we initialize the time also to 0. And we say, while y is greater than 0, or the time equals 0. Okay. So that way it'll run on that first time step, the time will be 0, it will run. And from that point on, y will be positive until it reaches the ground again. So then the second condition will be sufficient. All right, so that's the basic simulation loop. Let's just run that and see what we get as a result. And what I want to see here, actually, let's add one more thing. We'll need this later when we want to do a plot. Let's also update the time. All right, and the time is just adding that delta t or dt to the time on each time step. All right, so let's run this loop, and then, in fact, let's also display the final time. So this will tell us what the velocity is when the object hits the ground and how long it took for the ball to go up and then back to the ground. Set up the parameters, and then run the loop. All right, so you see that it took 6.3 seconds for the ball to go up and back to the ground, and it reached a final velocity of minus 31.8 meters per second. Now think about that. Does that make sense? Given that we had an initial velocity of 30 meters per second? And Dithya, can you see any problem with that? And I'll give you a little hint. Think in terms of conservation of energy.
So in this case, it seems like we have gained velocity.
Exactly. And this is a problem with the forward Euler method. It creates the illusion of energy being added to the system. And the fact that we have a substantial discrepancy here between the initial speed and the final speed, or you could say the initial energy and the final energy, means our time step isn't small enough. So let's try something a little smaller. Let's go maybe 0.05. Oops, I need to redo the initialization. Sorry about that. All right, so now you see it's getting closer to 30. And if I go even smaller, it'll get even closer. All right, so the smaller I make delta t, the closer it's going to get to 30, which is actually the correct answer. All right, so this illustrates how the time step needs to be small enough for you to get accurate results. Now, as far as doing the calculations, this is it. This is the whole simulation loop. But what I'd really like to be able to do is plot the results when I'm done. And that means I need to store the position, velocity, and time in arrays as I go along. So I need to add some indexing here. Now, there are different techniques you can use. In the previous example, we used a loop counter and used that for indexing. In cases like this, where we're running not for a fixed amount of time, but until a condition is reached, I like to use a different technique. I like to use the end keyword. You say y of end plus 1 equals y of end plus v of end dt. Now, some people really don't like this. It just seems odd. How can you set y of end plus 1 to something? Other languages would not let you do this. But MATLAB is very flexible. Okay, it says, oh, you want to add an element to the end of the array? Okay, I'll tack it onto the end of the array for you. Now, in terms of computational efficiency, this is a little bit problematic because this means that MATLAB has to reallocate memory every time, and that's a slow process. For what we're doing here, that's not a big deal. But if you're doing a really large, complex simulation, that could be a problem. And then you might want to allocate the memory in advance. That is, by dimensioning these arrays, setting them to all zeros, for example, in advance. Now, one more thing, if I'm going to, y is not going to be an array, I want this to be y of end, and this to be t of end. And we do the same with t here. All right, so now each time step, each time the loop executes, I'm adding on another element to the array. All right, I did everything right here. That should still work the same way. Okay, so I got the same results. But now I have t, v, and y in arrays, and I can plot. Now, there are different ways you could do this plot. We have two different things, velocity and position, that have different dimensions, so you don't want to plot them on the same axes. You want to plot them on different axes. You could do a subplot, or I think in this case what I'll do is a double y-axis plot. So I'll do y-axis left, and then I'll plot y versus t. And we recommend that you use control strings so that you have distinguishable line types. So let's do this one a black, let's just make it a black solid line. And it'll have its own y label, which is, let's just say height in meters. And then we go y-axis right, plot the position, I'm sorry, the velocity versus time. And let's make that a dashed line. Its y label will be velocity in meters per second. And of course, we need a title. And I'm going to say motion of a free-falling object. A mistake that people often make, or a bad practice, is for the title to simply be velocity versus time, or position versus time. That doesn't add any information. You already have that from the axis labels. You wanted to have something more descriptive that tells you what problem you're addressing here. So motion of a free-falling object, that's sufficient for right now. And since we have two data series on the same graph, we want to have a legend. The first one again was height, and the second one was velocity. So let's see how that works. There we go. All right, so now I've got the two curves on the same figure, same graph, but separate axes. Okay. All right, so Aditya, do you think I left anything out there? Anything I needed to explain?
Well, I just want to point out a couple of common errors that folks make when you are, doing the simulation, setting up the while loop, etc. The first thing is, as Jim said, it is a choice whether you want to use end or you want to use a loop counter. So like and then you'll make sure that you are incrementing the loop counter, because in a while loop, unlike in the case of a for loop, you are responsible for incrementing the loop counter. But one common thing that I've seen that students do is they use a combination of both. So they use both end and the loop counter. So my suggestion here is be consistent. So if you decide to use y of n is greater than 0 and y of n plus 1 is equal to so on and so forth, you don't want to also use I, because the compiler is then confused as to which exact variable in this vector, which exact element in this vector you're referring to. So you want to make sure that you're staying consistent throughout your code. The second thing is make sure you understand why the while loop condition is the way it is. Now, in this case, and in the case of our exercises and our application and in the final project, the simulation stops when, in this case, the ball hits the ground, or in the exercises case, the skydiver reaches the ground. But in other case, the while loop condition might be completely different, right? And so you need to make sure that you are being aware as to what the while loop condition is and why it is, in this case, y of n greater than 0.
All right. And just to kind of set you up for the exercise that we're going to talk about in a minute, how do you generalize this to some other problem? Well, the only things that will change from one problem to the next, the initial conditions might be different. So in the exercise, we're going to talk about a skydiver. So his initial height is not going to be 0. It's going to be whatever height he jumps from. And his initial velocity will be 0 because he's jumping from a standing start. And the other thing that may change is the acceleration. So when we introduce drag, the acceleration will no longer be constant. So you would generalize this by making this a of n. And for our problem then, the initial velocity of a would simply be g. And if necessary, bless you.
Thank you.
Another mistake that we often see, the acceleration is not a recursion equation like the velocity of position. It's not a of n plus something. That's not correct. It's simply you add up the forces, divide by the mass, and put in the expression for the acceleration at this moment, which in our simple problem here is simply g. And so keep that in mind. And one more little detail I want to address, because it may be on some of your minds, is g a positive number or a negative number? The answer is it's up to you. You can use either convention as long as you're consistent. You can either say g is a negative number and then the acceleration is g. Or you can say g is a positive number and then the acceleration is minus g, whichever you prefer.